Uh, before we start, let me just say, I think we are 1 minute early, so let me just talk about what I'm going to talk about today. I'm going to talk about locks, right? And we have already been discussing about locks, but I'm going to discuss a little more, and then I'm going to talk about condition variables. Okay. All right. So let's start. All right. So we had been talking about locks last time, right? And what were locks used for? Locks were used for mutual exclusion. What does it mean? It means that if there's a thread and there's some area of this that you want to make atomic, right? Then you would enforce mutual exclusion by putting an acquire and a release, right? And so this will become atomic, right? We saw many examples. For example, we saw shared data structures, like we looked at lists, and you can imagine other things also, right? Can be protected by locks. Similarly, shared variables, example, we looked at the hits variable in a web server, and any other shared thing, right? So any other shared object, the shared object could be a shared memory region, it could be a shared device, for example, a shared disk by multiple threads, or shared monitor, shared keyboard, right? If there are multiple threads which can access the same thing concurrently, you can put a lock around those access instructions, so that only one thread is actually accessing that resource or that memory region at a given point of time. Okay. Right. So let me give you one more concrete example to give you a nice understanding of how locks are used. So let's look at some web server. What is a web server? A web server is a server that takes your requests. So whenever you type some URL like www.iitd.ac.in, then when you type a URL, then let's say this is a client, right? That's using his browser. He is sending a request. Here is the web server. Right? So he sends a request. Usually the request is a URL, right, which says what page you want to access, and then the web server returns with a reply. And reply are usually contents of that page, right? So and this web server typically has a disk, right? So this is the disk of the web server that stores these contents, right? So the disk has files that store these contents, and whenever the web server looks at the URL, gets the contents of the corresponding file, and replies with its contents, right? So that's the web server. Okay? And of course, there could be multiple clients that are accessing it silently, right? Okay. So how is the web server written, right? So if you look at the code of a web server, you'll probably find something like this. Let's say it'll have an infinite loop. All right, and it will just say wait for message, Right? So it will just ask the network card to say, give me the next message. Then it will say read web page from disk, right? And then it will just say send reply. Right? So let's say 3 instructions. Of course, I'm writing these in English, but there'll be some code to do all this. Right? So wait for a message basically will say, let's look at the next packet that I've received over the network. Read web page from disk will actually read the web page from the disk, and then you will send the reply back over the network. Right? And if there are multiple messages coming in, they will just get queued. So there is some queue, and so messages are getting queued in this queue. Okay? And so when it says wait for message, the next message comes in to this server. Right? Okay, so let's say this is the network queue. Right? And then it reads from the disk and sends a reply. Now, you may know that the disk is a very, very slow device, right? So how does a disk work? Well, a disk is, so if you look at the disk, this is a magnetic disk, right? So if you look at how a magnetic disk works, it has multiple platters. It is organized as a spindle with multiple platters. Right? And this spindle rotates on its axis. Right? Each of these platters has what are called tracks. So these are tracks. Okay, and these tracks contain all the information, all the data, all the bytes. And then there's a disk head. So there's a head. That when the disk spins, it can read the data from wherever it is, right? And the disk head can actually, so this is the disk head. The disk head can move radially. Okay? So the disk head can move radially in this direction, up and down, so it can, you can read different things, and each platter has its own disk head, and so on. Okay, right. So that's how a typical disk works. And so because a disk has mechanical components, because things need to move left and right, so there is some motor there that needs to move, and motors are very slow, right? No matter how fast you build a motor cannot be as fast as a semiconductor, right? As a computer, right? Computation happens electronically. Electronic signals travel really fast at the speed of light. The motor is a physical device, so it cannot travel at the speed of light. It travels at some small speed, right? Typically, the access times of a disk are roughly 10 milliseconds, 1 to 10 milliseconds per access. Okay, so 1 to 10 milliseconds per access is the time it takes to read some data from the disk. All right. Let's compare this with how many instructions get executed in this time, right? So, if you buy a 1 gigahertz processor or 1 to 2 gigahertz processor, then how many instructions do you execute? So that means how many cycles? 1 to into 10 to the power 9 cycles per second, right? Or roughly 10 to the power 9 instructions per second. Right? So how many instructions can execute in one disk access, right? So one disk access is roughly equal to, let's say, 10 milliseconds. So number of instructions per disk access is equal to 10 milliseconds, that's 10 into 10 to the power minus 3 seconds, right, into 10 to the power 9, right, that's roughly equal to 10 to the power 7. So 10 to the power 7 instructions can be executed per disk access. So 10 to the power 7 is a very large number, it's roughly 1 to 10 million. 10 million instructions can be executed in one disk access. So disk access is really slow, right? So if you do one disk access, it makes no sense for the CPU to wait for the disk to respond, right? So in this code that we had for a web server, we look at this code, you wait for a message, this will happen really fast. If there was a message in the queue, then you will get the message within a few microseconds. But then this step will be really slow. Reading web page from the disk will be really slow, right? What could have been better thing to do, right? The better thing would have been to cache the web pages or cache the disk contents, right, in memory. Okay. So let me before I go on, let me just describe what a computer system looks like. A computer system has these are the bus, which is the communication medium. On the bus is attached a CPU and a memory. Okay, and then you have, if you have multiple CPUs, then you will have multiple CPUs here. And so on. Each of the CPUs will also have a cache. So each time a CPU accesses a memory location, it first checks its cache. If it gets it from the cache, it just gets it from here. Otherwise, it has to go to the memory, right? So CPU access latencies of the cache are roughly 1 to 10 nanoseconds, right? Access latencies of memory to CPU are, let's say, 100 nanoseconds roughly. Okay. And then on the bus, you also have devices, right? So let's say there is somewhere there is a disk. Right? The time it takes to go to the disk and come back is, we have seen, roughly 10 milliseconds. Okay. So the better thing to do is to, once you have read the disk contents, you can cache them in memory. Right? So whatever is there, you just cache them in memory, assuming that the same web pages are going to get accessed again and again. If those web pages are in memory, then you don't have to go all the way to disk. Right? So the memory can act as a cache for the disk. Right? And that way you don't have to pay this 10 milliseconds every time. Most of your requests will get satisfied by memory. Right? So you're optimizing for the common case where the same pages are getting accessed again and again, potentially by different clients or by the same client. And then so those requests can be satisfied from the memory. All right. Okay. So if I want to change my code to do this, so this was my web server earlier. Oh, right. So this was my web server earlier, and the problem was that this was very slow, and each time I have to go to disk. Instead, what I can do is I can say, okay, let's change my code, and let's say while true something. Right? Wait for message, just like before. Okay, and if page is not in cache, not in memory, then do what? Then page is equal to read from disk. Okay. Allocate a new page in the cache. So new dot name is equal to URL. New dot data is equal to page. Right. And this say new is equal to new plus 1. Right. And then you send reply, which will be the page. Okay, so what have you done? You've said that you'll get the message, you look at the URL, If the URL is in cache, then just get the page from the cache and just go here, right? So you are very fast. You don't need to go to the disk. So the whole operation will finish in few nanoseconds or few microseconds. You don't have to go to the disk. And so in the common case, assuming that your page is in the cache, you can just go directly, right? But in the rare case, when the page is not in the cache, in the memory cache, then you will go to the disk, read the page, and update the cache. So add the data to the cache, right? So this operation is just adding to the cache. All right, and then you reply. Okay, so this makes things faster, right? But does it really make things faster? Let's say there were 100 requests that have come in simultaneously, and the first 10 requests are satisfied from the memory. The 11th request is not satisfied from the memory, so it has to go to the disk. So this request has to go to the disk. Now it will take 10 milliseconds to finish. But all the requests that are behind it, all the 12th to 99th request, all those are just waiting for the 11th request to get finished. Although those requests could have been satisfied from memory, right? So it doesn't make sense. So even though you have this cache, because you have strictly serialized all your requests are going to be processed one by one. You take one request, process it. If one of those requests is a miss, which means you have to go to the disk, then all the requests behind it will just have to wait for a long time, right? unnecessarily. They should have really been executing while the disk was busy. They should have been getting satisfied, right? So ideally what you would want is that while the request is waiting on the disk, another request can come in and then get satisfied from memory, right? So other requests, this faster request can happen while the slower request is slowly moving on the disk. Okay, right? So let's go back to this thing. So the problem is that even for the few requests, so if there are multiple requests here, right? And let's say these requests are hits. Hit means satisfied from memory, but this one is a miss, right? Which means it needs to go to the disk. Right? Then even though the future ones are hits, they will have to wait. Right? So what, how can you solve this problem? Okay, so I'll open the floor for questions. Yeah, could somebody from the audience, from the students, tell me how you will solve this problem? Yeah, maybe you can just focus on this while somebody responds. Okay, good. So there's an answer from LNMIT. Thank you, LNMIT. Use multi-threading, right? So you will use multi-threading. You will basically have multiple threads. So let's say this function is called the server. Right? So let's say this function is called the server. You will basically spawn multiple threads. You will probably say for I is equal to 0, I is less than 10, I plus plus, thread create, server. Right? So there will be 10 threads that will get created, and each of them will be running this function called server. And each of these servers are going to execute this code. Right? So now if one of the threads is waiting on the disk, another thread can go on and get its request satisfied from the memory. Right? So one of the threads is waiting on the disk, another thread can still get satisfied from memory, and so you have much better performance of your web server. Okay, all right. So now my question is, but is this correct? Right? So if this code is run in a multi-threaded context, is it correct? And if so, how will you make it correct? Basically, I want to ask you, this code is correct if it's run by a single thread, but if multiple threads are running this concurrently, do you see a problem? Yeah, please focus on the. So somebody from the audience, is there a problem? Okay, LNMIT says Page should be thrown out of memory only if no other thread needs it. Okay, that's one thing. All right. So the problem is there's a race condition, right? So and what you said, LMIT is one example of a race condition. So there is a race condition here. What is the race condition? Two threads come in. Both the threads see that the page is not in memory, and they start allocating a page. So they start executing this code, which is these three statements, and they may be writing to the same cache location, right? The new value could be the same for both threads, and so now you will have problems. What kind of problems can you have? You can have you can have a lost update problem where one thread initializes new URL to something else, another thread initializes the news page to something else. Wrong URL is pointing to wrong page. That's a problem, right? These kind of bad things can happen, right? So what will you do to fix it? Well, answer is very easy. Given that what I've been studying, we'll use locks, right? So we'll use locks. And question is, how will you use locks? Which lock will you use? Like how many? So how many locks will you use? What will be the granularity of your locking? And where will you put these locks? Okay. Right. So one idea is that I can just say. So let's say, please, could you just focus here? So one idea is that in this code. So let me just rewrite this code. This slide has become really crowded. So in this code, I could say while true, and here there was wait for message, then if page in cache, if not page in cache, if not page not in cache, then read from disk, new dot data is equal to page, new dot URL is equal to URL, and new is equal to new plus 1, right? And then you will say send reply, right? So one option could be that I have one big lock. Let's say I have a lock called cache lock, a different color, cache lock, right? And here I'll put a call to acquire cache lock, right? And here I'll put a release. Okay, so that way you have made this whole thing mutually exclusive. If one thread is waiting here, then another thread cannot proceed. Okay, but is this correct? Is this correct? Well, this is correct, but this is not very this is not very very good, because the whole thing is still going to execute in a serial manner. This whole thing has become a critical section, so only one thread could be active here. So only one thread will be able to proceed here, and other threads will have to wait. Earlier they were waiting on the disk, now they will wait on the lock, right? A better thing could have been to put the lock here, right? This would be better, because if the page is already in the cache, then you don't take the lock, and so then you can just go forward and send a reply, and so then you don't have to wait. Okay. But even then you have some problems, because if there are multiple threads that need to access the disk, they cannot access the disk simultaneously, right? So it should be possible to say that multiple people should be able to access the disk simultaneously, and this code doesn't allow that, because you have one big lock around the read from disk function, right? So the even better thing would have been that you have a disk, you have a lock per URL, right? Or a lock per cache block, or things like that. So in general, you need to look at what are the problems. Then you need to figure out first you should figure out a coarse-grained locking strategy to make the code correct. Then you should worry about whether your coarse-grained locking strategy has actually improved performance. Because in my first example, when I put the lock around the whole thing, then it was as good as my first code, which was having no multi-threading, right? So locking makes the does not annuls or nullifies the advantages of multi-threading, right? And you should avoid that. So you should make sure that you still have the advantage of multi-threading, and yet your code is correct, right? So in this example, if I put an acquire lock here, then I'm completely nullifying all the advantages of multi-threading. But if I put it here, then it's slightly better, right? But you have to be very careful, because this check should be correct, right? It shouldn't happen that you have checked that the page is in cache, but by the time you actually start reading the page, it has been removed by this code, right? So in general, you have to be very careful when you are doing doing locking, and these things basically you learn by practice. So I would highly recommend that you write code which involves lots of different locks, and I have given you some assignments. I've given your instructors some assignments to do, and I would highly recommend that you do them. Okay. All right. Among other things, I would like you to implement a small web server for yourself, and change its, first implement a single-threaded web server, make it working, then implement a multi-threaded web server with coarse-grained locks, make it working, then improve its performance by making the coarse-grained locks into finer-grained locks, right? And I can assure you that this will be a very enriching exercise, and you will learn a lot about how to use locks and how to do multi-threading in general. Okay, all right. So let's move forward. So now next I want to talk about condition variables, or condition variables or also known as conditional synchronization. Right. Okay. So first let me just give you an example where so this is so locks allow you to do mutual exclusion, but there are other types of synchronization that are needed in a computer system. So in the example of a web server, we were looking at the disk, and we said let's disk is very expensive, let's have a cache on top of the disk, but then if there are multiple threads, but then having just a cache is not enough, you also need multiple threads. But then when you have multiple threads, then there are problems of synchronization. Then you have problems of synchronization, you put in locks, but when you put in locks, you are back to square one. But so you should put in finer grained locks, then you put finer grained locks, then you have to worry about correctness problems. But so the best solution would be to use finer grained locks and carefully reason about its correctness, right? And modern web servers, for example, will always typically do this kind of thing, right? Now there was another piece of the web server which was a network, right? So when I said wait for network or wait for message, there was a message coming from a queue, right? So in this example, there was a queue, right? And there was a network. There was a thread, which was a network thread that was putting elements into the queue, right? And there was the server thread that was consuming elements from this queue, right? So this was the producer and this was the consumer, right? So once again, you had to organize your system such that there was a separate thread which was actually implementing the network device driver and other things and reading data from the wire and putting them in memory. And then there was another thread called server which was reading things from memory and putting it in and actually processing the requests, right? And you needed to do this because if you put this network device driver in the server, then you will lose a lot of packets because the server thread is going to take a lot of time in processing these requests, potentially because it has to access the thread, whereas you want that all the packets that are coming in should immediately get queued into the queue, right? So the network thread just takes packets from the wire and puts it in the queue, and it's fast, and so packets don't get lost, right? It's not that some packet is coming on the wire and there's nobody to read it, right? So network thread is making sure that those packets are getting read and those are getting put into the queue, and then the server thread, which is slower, is reading from this queue. All right. Okay. All right. So let's see, how this code is written between network and server. So in this case, the network is called the producer, and the server is called the consumer, right? Right. So now obviously this queue cannot be infinite, right? So the queue will have some finite size, let's say maximum, max length. Right? So that's the maximum size that this queue can have, max length. Right? Well, let me just call it buffer size. Okay. All right. So let's see how this code is written. The network pack. So there will be two threads. One will be the network thread, right? And simultaneously there will be a server thread that's running. Right? What is the job of the network thread? Just read from wire. Okay. Put packet in queue, right? Let's say it has a count which maintains how many packets you have put in the queue, right? And that's it. Okay. And there's a server thread which is basically doing what? It is doing get packet from queue, right? And decrement this local variable called count, global variable called count, and say count is equal to count minus 1. Okay. Now, is this code correct? Well, what are some bad things that can happen? Well, some bad things that can happen is, let's say the queue is empty, right? So the queue is empty, then what should happen? The get packet from queue should not be called, right? So instead of just doing this, maybe what I'll do is I'll have some code which will say if count is equal to 0, wait. Right? Okay. So the server will wait if the count is equal to 0. and as soon as the count becomes non-zero, if the count is non-zero, then it will get the packet. If it is equal to 0, then it will wait. Okay. What does wait mean? Wait will basically mean it will just suspend itself, or it will just keep, yeah, it will just suspend itself, right? So wait is just saying that, you know, I don't have anything to do. The queue is empty. I can just suspend myself. I can go to sleep. That's what wait means. Go to sleep, right? But it should not sleep forever, right? So when should it wake up? It should wake up whenever the network thread produces some packet. Right? So as soon as the network thread produces a packet, it should wake up or notify the server, right? So whose responsibility is it to notify the server or to wake up the server? The network thread, right? So the network thread should notify the server. So let's look at it here in the code. Okay. So when you say count is equal to count plus 1, you can check if count is equal to 1, which basically means initially it was 0 and now it has become 1. So you can imagine that the server may be waiting. So you can say notify. Right. So here you said if count is equal to 0, wait. Here you said if count has just become 1, then let's notify the server, right? So if it was waiting, then it should wake up, right? It's like making a phone call to the server saying, if you're sleeping, please wake up because I've put in more data. If I don't do this notify, then the server will just wait or sleep forever, right? And that we don't want that. Okay. Okay. So this is one way to do it. Notice that this is also communication between or inter-thread communication between the network and the server threads. This kind of communication is not mutual exclusion, right? You're basically telling somebody to sleep, wait, somebody who's waiting to start, right? So for this, locks are not enough. You need something else, right? That's one thing. All right, okay. The other thing is, similarly, it's possible that the buffer has become full, right? So the network thread is running, but the buffer thread has become full. So the network thread has read from the wire, it's wanting to put the packet in queue, but the buffer has become full, right? So if the buffer is full, then it shouldn't be putting a packet in the queue. So what should you do? Should add some code here. Say if count is equal to buffer size do what? Wait. Okay. So even the network thread, the producer thread can say, if the buffer is full, I should wait. And the consumer thread should similarly notify the producer if count is equal to what? Buffer size minus 1. Notify whom? The network thread. Right? Okay. So my question is this code correct? Right? So what am I doing? Each thread checks. So the producer thread will check if the buffer is full, then it will wait. And the consumer thread will check if the buffer is empty, then it will wait. And similarly, both threads are also responsible for waking up the other thread if the buffer has just become not empty, or if the buffer has just become not full, right? Yeah, please focus on the code so that they can look at it. Okay, so my question is this code correct? So the answer is no, this is not correct because this code also has race conditions, right? So let's look at the let's look at what kind of race conditions that can possible happen. Well, let's say that this server thread has just checked whether the count is equal to 0 or not, right? And let's say the count was 0, so it has checked that the count is equal to 0 and it is just about to go to wait, sleep, right? So it's going to go to wait, but before it goes to wait, the network thread wakes up and puts a packet into the queue, increments count and calls notify. But the notify got called before wait, right? If the notify happened before wait, then the network thread has sent its notify, but the server thread hasn't received it because the server thread says, oh, the notify has come, but I'm not waiting, so I don't care. Then it goes to wait, and now what will happen? It will wait forever because the count, the network has already sent its notify, and you won't see another notify. Okay, let's look at it more concretely in writing. So this code has a lost notify problem. What is the lost notify problem? Server checks count, which is 0, about to go to sleep by calling wait. Right? The second thing that happens is network produces a packet increments count to 1, right, and calls notify. Because server has not yet called wait, the notify gets lost. Right? And then fourth, server calls wait and sleeps forever. Okay, so what can happen between the check of whether I need to go to wait or not and the actual waiting? If the network thread gets to run in the middle, or the other thread gets to run in the middle, then the notify gets lost, and so the first thread will have to sleep forever. Will end up having to sleep forever, and that's a bad situation. Your system will deadlock. It will not make any further progress. Okay. So I want you to look at this, understand this, and if you don't understand it, please ask me questions. Right. So I'll leave the next 5 to 6 minutes for questions. Okay, so notice that because the meaning of the semantics of notify is that if the thread is waiting, then it will get woken up. If the thread is not waiting, then the notify has means nothing. It just it's a it's like saying you want to wake up somebody. If somebody was sleeping, then he gets woken up. But if he's already woken up, if he's already awake, then waking him up makes no sense. So in this case, what has happened is that one person decided, checked some condition and said, oh, so it's like saying that one person checked what's the time. He said, oh, the time is actually 9 p.m. It's time to sleep. So he's just about to go to sleep, and so the other thread comes in and he changes the time, and he changes it to 9 a.m. and he tells the other guy, oh look, the previous night has gone and it's a new day, but by that time I have decided that I'm going to sleep, right? So he has sent me a notify saying he's trying to send me a wake up call, but because I was not sleeping, I ignored that wake up call. I said it's some bogus wake up call. I went to sleep after that, and I kept sleeping forever because the person who was supposed to wake me up, he thinks he has done his job. He has woken me up, and I think that somebody should wake me up, only then I will wake up. And so we have a problem. We both threads don't make any useful progress. The thread which sleeping keeps sleeping. The thread which is supposed to wake him up eventually will keep running till its buffer gets full, and now then it will go to sleep, and now ultimately both threads will go to sleep, and you'll have a deadlock in the system. All right. So what did you want? If you look at this code, you wanted that this check and going to wait decision should be atomic. All right. Similarly, this check and going to wait decision should be atomic. Okay. So how do you make it atomic? Right. Notice that this kind of synchronization is different from just using locks, because I also need to do wait and signal, right? So this notify is signaling this, and similarly this notify is signaling this, and we need to do it in an atomic fashion. All right. So we are going to use locks to do this, but just locks are not going to be enough. We are going to have to use what are called condition variables. Right. What are condition variables? Well, condition variables are also variables just like locks. So there will be some struct like struct condition variable CV, let's say, right? And it will have two functions, void wait struct CV star, okay, and void notify struct CV star. Notify is also called signal. Right, and also called also known as wake up. Okay. The wait, recall that we wanted that the wait, so the semantics are that if one thread can start waiting on a condition variable, which means that it'll just keep waiting or it'll go to sleep till some other thread calls notify on that condition variable. And when it calls notify, it get woken up and it'll come out from its sleep state, right? except that we also want that this should happen atomically. So the wait function takes another argument, which should be a lock. Right. The semantics of wait are that it will check the it will go to sleep and release the lock atomically, right? So it will go to sleep on this condition variable and it will release the lock, and it will do both these things atomically. The semantics of notify is that it will wake up any thread that's waiting on this condition variable. The notify system call does not take a lock argument. Okay. Right. So I'm going to discuss more about condition variables and what they mean and how they are used. But I would highly recommend that you also do some background study on what are condition variables and how they are used. Okay. In fact, to many of you, I have given this hare and tortoise assignment, and there you may want to use condition variables to do synchronization between hare and tortoise in a multi-threaded scenario. Okay, so I'm going to discuss wait and notify next time, which will be Wednesday. Thank you.